Raz will tell us about the gravity of fluid dynamics.
Okay. Is the mic on? Yep. Okay. Excellent. So, in the first two lectures of this little course, I described to you the structure of the equations of hydrodynamics, and told you about the outstanding questions of the complete set of constraints that constrain constitutive relations of the equations of hydrodynamics. Something I would have liked to do, but I almost certainly will not have the time to, and will not try to do now, is to describe the generalization of what I was saying to the hydrodynamics of superfluids. There's an interesting story there, an interesting and more elaborate story there, which we may return to right at the end of these lectures. But I'm now going to follow the plan of my course, which was to divide the lectures equally between hydrodynamics and gravity, and move to the study of gravity. Okay, now you might wonder why I'm studying gravity in the context of hydrodynamics. Of course, this audience is not wondering, you know. The context of this of the connection between these equations is Maldasena's famous, at least the inspiration between the connection is Maldasena's famous ADS-CFT correspondence. Okay, so I'll remind you that Maldasena has explained to us that in several examples there's a duality between the dynamics of a quantum field theory and the dynamics of a theory of gravity in one or more higher dimensions. And the canonical example of this is the duality between n equals 4 super Yang-Mills theory and 2b string theory on ADS 5 times S5. Well, what does all of this have to do with hydrodynamics? Once you start thinking about this duality in the context of hydrodynamics, something occurs to you. You see, I told you that the equations of hydrodynamics are a long wavelength effective description for the dynamics of any quantum field theory under certain circumstances. The certain circumstances being local equilibration. Okay? Now, n equals 4 Yang-Mills is a quantum field theory. So, if everything I said on general grounds applies to every quantum field theory, it should in particular apply to n equals 4 Yang-Mills theory. Okay? So, we know on general grounds that n equals 4 Yang-Mills should admit under certain circumstances an effective classical description in terms of the equations of hydrodynamics. Okay? As we've seen before, the operators that play the most important role in hydrodynamics are the stress tensor and some charge currents. Okay? So some effective classical description of the stress tensor and perhaps in some situations some charge currents should be described by the equations of hydrodynamics. This is what we've reviewed over the last two lectures. However, Maldasena's correspondence tells us something much more and much more detailed and much more interesting. It says that there is an effective classical description of n equals 4 Yang-Mills theory for all processes, not necessarily slow processes, not necessarily near equilibrium processes, just for all processes. There's a new effective description of n equals 4 Yang-Mills theory in terms of some other classical equations, and these are the classical equations of 2b string theory. Okay, so you put these two statements together, and it must mean that the effective classical equations of 2b string theory on ADS 5 times S5 under appropriate circumstances reduce to the equations of hydrodynamics. Okay? This must somehow be true, and it leaves you with many questions. Okay? The questions include, is it true? Can you show it? And if it does so, if this reduction does happen, with what value, with what constitutive relations? Yeah, so we spent a long time in the first two lectures talking about the allowed forms of constitutive relations. That was just allowed forms and general considerations. Now you take a particular theory, you'll have a particular constitutive relation. Can you compute the constitutive relation of the n equals 4 Yang-Mills fluid? Okay, now as you all know, the ADS-CFT duality has two parameters. There's n that controls how quantum the bulk is, and there's lambda that controls how stringy the bulk is. Okay? While I would love to be able to work out what I'm saying at arbitrary lambda and arbitrary n, and I think there's a lot of very interesting stuff, even conceptually, about that, which we'll turn to in the last lecture perhaps. At the moment, you know, I'm limited by technical ability to work with what I can work with. So what I'm going to work with is the n goes to infinity limit, so that the bulk becomes classical, and the lambda goes to infinity limit, so that the equations in the bulk are well understood tractable equations, the equations of 2B supergravity on ADS 5 plus S5. Okay? Remember that the prediction that we reduce to the equations of hydrodynamics is true for any quantum field theory, so it should in particular apply to these particular limits of n equals 4 Yang-Mills. Okay, so now the implication of the ADS-CFT correspondence for hydrodynamics becomes sharper. It becomes the statement that the equations of 2B supergravity on ADS 5 cross S5 must, under certain circumstances, reduce to the equations of hydrodynamics in 4 dimensions with some particular constitutive relations. Can we show this? Can we compute the constitutive relations? That's the question. Okay, now this question is already seems, even with this simplification, seems a little more formidable than necessary. Seems a little more formidable than necessary because, as you all know from the general rules of the ADS-CFT correspondence, there is a one-to-one correspondence between fields in the bulk and operators on the boundary. And there's if you take all the fields of 2B supergravity and Kaluza-Klein reduce on the S5, you get an infinite number of fields in ADS5, corresponding to the fact that even in this weird lambda goes to infinity limit, which sends most of the operators of Yang-Mills theory off to heaven, even in this weird limit, there's an infinite number of operators in the theory. However, hydrodynamics is the dynamics of very particular operators. So you might wonder, can we do better than deal with this whole shebang of 2B theory on 2B supergravity on ADS 5 cross S5? Now we're doing classical physics, so we want to make that statement precise. How can we do better than dealing with some big theory? Well, in classical physics, there's a time-honored way. You look for a consistent truncation to the equations of motion to a smaller sector that includes all the physics of interest. So just a minute about consistent truncation. What do I mean by consistent truncation? It's a very simple idea, but often used in very complicated contexts of supergravity. So some of you may have got intimidated by this simple idea in those complicated. Let me just explain what a consistent truncation is. Okay, suppose you've got a classical system with two kinds of degrees of freedom. Let's say x and y degrees of freedom. And this action, the action that describes these x and y degrees of freedom, has the following form. There's some action for x plus some, let's say, sx of x plus sy of y plus some interaction between some s interaction. But this s interaction has the feature that it has an explicit power of x square multiplying some otherwise arbitrary function of x and y. Okay, that this is a power of x square, not a power of x. What does this mean? When this situation happens, there's something very simple you can say about particular solutions of this dynamical system. What you can say is the following. Look, suppose, now suppose you've got a solution to the equations of motion of suppose we've got a solution to the equations of motion of this Lagrangian, just Sx of x, okay? And for simplicity, I'll choose the value of the solution to be x equals 0, just by shifting whatever the solution is to x equals 0. Okay, it's in that language that I've put x square. Okay, now I'm claiming the following. Give me an arbitrary solution to the equations of motion that follow from sy of y, Okay, give me an arbitrary solution to the equations of motion that follow from Sy of y. That solution, along with the statement x equals 0, is a solution to the full equations of motion. Why is that? That's because when you vary this action to get equations of motion, when you vary with respect to y, you get something from here and something from here, but that something from here is 0 because it's multiplying x squared on the solution you've chosen. When you vary this action with respect to x, you get something from here and something from here, but because there was an explicit x square, not an x, this is also 0 on the solution you've chosen, namely x equals 0. Okay? So whenever you've got a classical Lagrangian with this form, interaction terms start with x squared, a squared in x. You are allowed to classically look at solutions, just forget about the x, set x equals 0 and look at the action, the part of the action that depends just on y. Okay? Whenever this happens in classical physics, it's the reduction of this full action to the action that governs just the equation, just the dynamics of y, is said to be a consistent truncation of your system. And this happens all the time in supergravity theories. Okay, so what I'm going to do now is to search for a consistent truncation of the equations of type 2b supergravity on ADS 5 cross S5 that contains the physics of interest. It contains the please.
What is the extent of fermionic fields?
Well, fermions always appear quadratically. So setting fermions to 0 is always a good thing. Yes. Just Lorentz invariance. Yes. Okay. Excellent. So I'm going to search for a consistent truncation of the equations of supergravity to something that contains the physics of interest. So the first part of my talk, I'm going to be looking at just uncharged hydrodynamics. Okay, hydrodynamics without an extra conserved U1 charge, just to have the simplest case first. Okay, so I want something that has only the dynamics of the stress tensor. We know according to ADS CFT that the stress tensor is dual to the metric. So what I would like is a consistent truncation that keeps only the dynamics of the metric field in ADS 5. Is there such a consistent truncation? Yes, there's a consistent truncation to a very simple action, which is square root g r plus 6 in appropriate units d5x, Einstein's action with the negative cosmological constant. Now the value of the cosmological constant is arbitrary because you can scale it by changing your units of space, because this guy has 2 derivatives and this guy has none. And I've chosen a convenient value. With this choice, ADS will turn out to have radius 1 in my solution. Okay? Excellent. Now, first here, I've just asserted for you that that this set of equations is a consistent truncation to the equations of type 2b supergravity. However, actually, this being a consistent truncation is true of a much wider class of theories than 2b supergravity, and I'm going to take 2 minutes to explain that to you. Okay? A large set of theories satisfying very reasonable conditions all admit a consistent truncation to Einstein's action with a negative cosmological constant, as I'm now going to explain to you. Okay, so consider some sort of theory which has the following properties. Okay, the properties are A, it admits ADS 5 as a solution. Okay, so you should think of this theory as a theory of gravity in 5 dimensions plus perhaps an infinite number of other fields, for instance dimensional reduction of some supergravity theory, but it admits ADS 5 as a solution, ADS 5 at some particular values of all other fields as a solution. B, the theory is 2 derivative. And C, the unique uncharged spin 2 field is the graviton, and there are no fields of spin greater than 2. I'm going to demonstrate that all such theories admit a consistent truncation to Einstein's action with a negative cosmological constant. Yes?
How important is the 5 in ADS 5?
It's not important at all. It's just an example. Okay. Okay. Before I start the demonstration, let's just look at the reasonability of these assumptions. Firstly, it admits ADS5 as a solution. Of course, we want to look at such theories, dual to conformal field theories. The theory is 2 derivative. This would be true of any theory that you get by dimensionally reducing some higher dimensional supergravity. So it's true of basically every well understood example of ADS CFT that we've studied. Okay? The third assumption is the most tricky. We assume that there are no fields of spin greater than 2. That's also true of any compactification of supergravity. But we also assume that fields of spin 2 are unique in the sense that if they're other than graviton, if there are spin 2 fields, they're charged under some other symmetry. Okay? So that these fields cannot appear linearly. Okay, they have to appear at least quadratically. This is true basically of every example that I know of the ADS CFT correspondence. So anyway, with a reasonable set of assumptions, I'm going to show you this consistent truncation works. Let's just start without further ado. Okay, let's see. So what I want to do is to try to divide the degrees of freedom of my theory into the graviton degrees of freedom and everything else. Okay? So I'm going to write down the most general action I can imagine. Okay, so I'm going to write down an action that goes like R times some function of other fields plus square root G times some function of other fields. Okay. Now, the kind of term I'm not going to write down is a term like R mu nu, A mu nu. Okay. That's because we've assumed that there's no other spin 2 or higher spin field in the problem that can appear linearly, because it's not forbidden appearing just by itself by symmetry. Okay. That's going to be very important. This kind of term I will not write down, R mu nu alpha beta, A mu nu alpha beta, for the same reason. Okay. Now, with this assumption in hand, the demonstration is very simple. Look, the first thing that in order to check that we've got a consistent truncation to Einstein's action with a negative cosmological constant, we basically want to show that that there are no linear terms in other fields coupling to R and square root G. Okay? Now, the only linear terms in other fields that could couple to R and square root G, because both R and square root G are scalars, are scalar fields. So all fields which have higher spin we can just forget about right from the beginning. Okay? So what we're worried about is that there might exist some sort of linear scalar, or in a basis of all possible scalars, AI times R plus square root G in the same basis, phi I times Bi. Okay? But now suppose this happens. What I'm going to do is redefine my metric to get rid of the scalars from behind here. I move to the Einstein frame. This I can always do. Okay? Once I move to the Einstein frame, I get an action that's square root G times R plus, some number of scalars, Ci times phi I times square root G. And then I use the fact.
You might get something that's
What?
Don't worry that the scaling the metric is something indefinite, might not be a metric after that.
With something indefinite might not be a metric. Firstly, this would have. I'm only worried about this linear term, but there's also an R term here. So this R. I'm just taking whatever function of the scalars appears and expanding it. Okay, and then it's this combination that will appear in the metric. These phi's are supposed to be small because it's 1 plus something small, so this will never be a worry. But basically, I'm asserting that we can move to Einstein frame in this dimension.
You presumably would allow high derivative terms.
I'm not allowing high derivative terms. If I allowed high derivative terms, this will break down, as I will say.
But in string theory,
In string theory, yes, but not in supergravity. So not in the lambda goes to infinity limit. So in string theory, this statement that I make will not be true, as you will see. But in the lambda goes to infinity limit of every example of ADS-CFT that we've seen, it is true. Yes. So that's a very important point, and we'll come back to it.
Sorry, can I? Why do you only consider scalars? Can you have scalars formed from higher spins?
You could have scalars formed from, let's say, a spin 1 field, but then it would be quadratic. A mu times A mu doesn't worry us for consistent truncation, because quadratic couplings are okay. It's only linear couplings that we worry about. Okay? And now that we have this form of the action, let's use the fact that we know that ADS5 is a solution. So we solve for the equations of motion with respect to the phi I fields. Square root g is non-zero in ADS5. So we get the consistency with ADS5 being a solution requires that AI is equal to 0. Okay? So none of these terms can appear. So in Einstein frame, we've got a consistent truncation to Einstein's equations with a negative cosmological constant. Let me emphasize what I've used here. I've used, as Michael correctly pointed out, I very, very importantly used that we are in a two-derivative theory. For instance, suppose we had square root g r plus constant plus r square. I could use the maneuvers that I used to move to Einstein frame here, and then I would have some scalar coupling to this and some scalar coupling to that. In ADS5 space, this and that take particular values. So what I would get from the requirement that ADS5 is a solution, I would get some linear combinations of the coefficients that multiply this and the coefficients that multiply that vanishes. But the coefficients will not individually vanish. This would be enough to ensure that ADS5 is a solution, but arbitrary metric fluctuations would then source these other scalar fields. Okay? So I've crucially used the fact that we have two derivative gravity, and then we don't have fields of other fields of spin 2 or higher, other than perhaps with charge. Okay, so this is a limited statement. It works only given a host of assumptions, but it's not as limited as you think, because it applies to the supergravity limit of every example of ADS-CFT that I'm aware of. Okay? What does that mean? What it means is that everything I'm going to be saying over the next hour applies not just to n equals 4 Yang-Mills theory, but applies to the hydrodynamics of every example of ADS-CFT that has been written down so far in the supergravity limit. Okay? This, as you know, is an infinite number of examples. These infinite number of examples are very different field theories, very different Lagrangians, very different operator contents, but what we have deduced here is that they have a universal subset of dynamics for the stress tensor. I emphasize something else for those of you who've grown up with worldsheet conformal field theory. Some of you are thinking, that's old stuff. In 2 dimensions, I know this is true, so maybe it's just a property of conformal invariance. As some of you know, stress tensor correlators in a 2D conformal field theory, completely universal. They're determined by the central charge, they care about nothing else. Okay? That is in general a statement that is true only of 2 dimensions. It's not true of n equals 4 Yang-Mills at weak coupling. Okay? There is no consistent truncation to the stress tensor sector at n equals 4 Yang-Mills at weak coupling. But miraculously at strong coupling, we get this universal, consistent, universal, autonomous dynamical sector, and it's not just some random stuff, it's governed by Einstein's equations with a negative cosmological constant, perhaps the most beautiful equations of physics. Okay, so something really beautiful is going on. In this extreme strong coupling limit, we see an emergent universality for the dynamics of the stress tensor. Everything I'm going to be talking about in the next hour will lie within this universal sector, so it has more universal applicability than just n equals 4 Yang-Mills, though it's limited universality. It does not apply to all conformal field theories. It does not apply to n equals 4 Yang-Mills at strong coupling with alpha prime effects violated, but it does apply with some degree of universality, it's strong coupling. Okay, so this is something to keep in mind. So,
I mean, is this going to be a condition if there's a holographic dual, in the sense that
no.
because it looks like because you've got this universal sector that's T mu nu, then that's the
No.
gravity sector in some sense.
Yes. So, it's not physically necessary that there is a universal sector. You could have had, let's say, a Lagrangian like this with some f of phi. There's nothing wrong with that. Okay? It's just somehow beautiful that it happens, that there's a universal consistent truncation to gravity. But alpha prime effects certainly spoil this. You can explicitly find alpha prime effects that break this consistent truncation. Okay?
Alpha prime effects, you mean 1 over n corrections?
No.
Then what do you
High derivative terms. Just
They come from what, lambda? Or
lambda, yes. Going away from lambda equals infinity spoils this consistent truncation. So, you see, if you jiggle around with the stress tensor, it will excite all the other fields generically. Only at lambda equals infinity will it not. Okay, please.
So maybe this is also somehow related to the hydrodynamic limit, because in the hydrodynamics, we truncate higher derivatives. And if the interaction is very strong.
Okay, good. But it's very important to distinguish two different things. There's the derivative expansion of hydrodynamics, which is a derivative expansion on the boundary. And there's the derivative expansion of string theory, which is a derivative expansion in the bulk. From the point of view of the quantum field theory, the derivative expansion of string theory is controlled by lambda. Okay, it's going away from infinite coupling. Okay, it applies to all processes, short wavelength, long wavelength, everything on the boundary. The derivative expansion of hydrodynamics is completely conceptually independent. And any value of lambda, you could try the hydrodynamic expansion. These are unrelated expansions. Okay, the string theory derivative expansion is a coupling constant of the field theory in which you do a long wavelength expansion. Okay, please.
So this truncation gives you some solutions to the classical equations.
Yes.
How do you know it's the one you want?
How do we know it's the one we want? Okay, you see, what we are interested in is the motion of the stress tensor. Okay, and since this governs autonomous motions of the stress tensor, it seems very likely.
Okay, but because I suppose it's just I know the basic thing is just something else could.
What?
One of the other fields could pick up.
Well,
Something which would then affect the equations of the stress tensor to give you and break this universality.
okay, let me give you a slightly better answer to the question you asked. Every other this answer will make more sense as we go along, but let me say it anyway. Apart from charge fields, in the case that we excite things with charge, it's not the solution we want. Okay, but every other mode in the theory, the quasi-normal modes of the spectrum are gapped. That's actually why we know that this is the sector. This is the sector that contains this, and the charge contains the only ungapped quasi-normal modes. This is really the reason we know this.
This works for the sitter.
Presumably.
Any solution, I think.
Presumably, yes. As long as you have, right. I think so. Yes.
So you started by explaining that the supergravity theory was living on ADS5 plus S5, but the lower dimensional theory that you get, it's only for the ADS parts.
Yes.
How consistent is it to forget completely about this sphere?
This is the argument that tells you it's consistent. You see, you can think of the theory on ADS5 plus S5 as a theory on ADS5 with an infinite number of other fields. And this argument tells you can forget about all the other fields. It's a consistent truncation, yes?
Maybe I missed it. If this is valid for lambda equal to infinity,
yes.
So can you look at corrections in 1 over lambda which are corresponding to the 1 over n correction? Can you make that statement? Or
in 1 over n correction?
Lambda and n.
You could look at both, okay? Now the 1 over lambda corrections are conceptually straightforward. As you will see as we go through our procedure, conceptually what you have to do is clear. The 1 over n corrections are much more interesting. Okay, because at least if you're at finite n, there's no sense in which you should be solving classical equations. Okay, then there's a whole shebang of issues there that one could try to open. We'll postpone that to the part I don't know part of the lectures. Right. Okay. Yes.
I thought you said it might work for de Sitter also, right?
There's consistent truncation.
But then,
I'm not saying hydrodynamics works.
Okay, but if you turn off, lambda completely, for Minkowski or flat space or whatever. Sorry, you know what I'm trying to say.
Yeah, presumably it works in flat space as well. You know, under appropriate assumptions. Maybe even better. Okay, I've only carefully thought through anti-de Sitter. I suspect it's a very general thing with, okay, good. So, armed with this result, we're now going to forget about 2B theory and ADS 5 cross S5 and look at the much simpler theory, which I wrote down for you, which is square root G R plus 6. This is a pretty simple theory. This is the theory we're going to work with. Okay, now what do I want? My aim is to see if the equations of Einstein gravity with the negative cosmological constant somehow reduce to the equations of hydrodynamics on the boundary. Now let's remember the relevant parts of what we learnt about hydrodynamics. What is hydrodynamics? Hydrodynamics is the dynamics of locally equilibrated stuff. Okay? So before we start trying to find the gravity dual of locally equilibrated stuff, obviously we want to remind ourselves of what the gravity dual of globally equilibrated stuff is. Well, this you've seen about a zillion times in this school. It's the favorite transparency, the metric of a black brain, usually with charge, usually extremal, but anyway, we'll be simple-minded here. Okay, it's the metric of just an ADS Schwarzschild black brain. The metric that Witten informed us, you know, a month after Maldesena's ADS CFT paper is the dual to thermal physics. It's very simple. It's given by f of r dt squared plus dr squared by f of r plus r squared dxi squared, where f of r is equal to r squared in a 1 minus pi t to the 4 by r to the 4. T is the temperature of the black brain. Okay. Okay. So what can I say about the solution? You know a lot about it. You've seen it a lot. But anyway, just for completeness, firstly, this solution is asymptotically ADS. What do I mean by that? I mean, if I go to large R, I can forget about the 1 over r to the 4 here. Then this metric becomes r squared, so reduces at large R to r squared to minus dt squared plus dx squared plus dr squared by r squared, which is the metric of ADS space in Poincare patch coordinates. This metric is asymptotically ADS. It differs at large R from this metric only by terms of order 1 over r to the 4, which turns out to be the right criterion in appropriate coordinates. Okay? According to the rules of ADS CFT, that means it represents a state in the conformal field theory. Okay? The second important thing about this metric is that while it reduces to ADS at large R, at small r it differs significantly from ADS. And the place where it really starts differing is when r gets near pi t. Because then this guy has a 0. This is something you're familiar with. The 0 of this and the infinity of this is the fact that we've got an event horizon. Okay? So this is a space with an event horizon. Now this event horizon, unlike the event horizon of a black hole, is not localized about a point in space-time. It's translationally invariant in the field theory directions. Our metric has a killing symmetry for x translations. The event horizon exists everywhere. Okay, that's why it's called a black brain. Okay, because it's got an event horizon. This solution is thermal. It's associated with the Hawking temperature, and I've chosen my parametrization of the solution so that the Hawking temperature is the parameter T. Okay, Witten, for obvious reasons, identified this as the gravity dual of taking n equals 4 Yang-Mills, or as we have just seen, any example of ADS CFT that has a supergravity limit. So thermal equilibrium is in this universal sector. Okay, taking this field theory and putting it at temperature T. Okay, so that's simple. We just have to appeal to Witten, and we know what the dual to global equilibrium is. So it sounds like we're making progress. Now we want to find the dual to local equilibrium. Okay, now how do we find? Well, firstly, you might think we've not done well enough here. Not done well enough here because we've looked at we've found the dual to equilibrium when the stuff is at rest. As we've seen, in order to understand fluid dynamics, we need to look at things moving. But of course, it's easy to put this stuff in uniform motion. All we do is boost it. Okay? So a more covariant way of writing this, this solution, a better way of writing the same solution after a boost coordinate transformation is the following. Where u mu is any 4 vector normalized to -1, and p mu nu is the same thing that we had in our first few lectures. It's the projector onto space. Okay? And it's clear that if you take this metric and set u mu equals 1, 0, 0, 0, you reduce to this metric, but a boost takes you from that to any value of u mu. Okay? So as long as u mu is a constant, if this is a solution, that has to be a solution, it's just a coordinate change. Okay? So now this is the solution that represents global equilibrium in uniform motion. That's pretty simple. Now, what is the solution that will represent local equilibrium? Well, locally what we want to do, as we've discussed, is look at things that are locally equilibrated, but such that the equilibration parameter varies around. So, something that you might suggest itself is the following. You might wonder, well, suppose I start looking at a metric as a starting point in some perturbative expansion. We'll get to what expansion very soon. But suppose I start looking at a metric that looks like the same thing here, except that I make the velocity a velocity field. Let it vary as a function of x. So this projector would also become a projector field, and the temperature also becomes a function of x. By x I mean both space and time. Okay? You might think maybe this is a reasonable approximation to the metric of a fluid moving with velocity u mu of x and temperature T of x. Okay, as I'm going to try to tell you, this idea is a good one. It's almost right, but it's not quite right. Okay? And in order to see why it's not quite right, it's useful to think about what we've done here in slightly more geometric terms. You see, we've got a boundary in ADS-CFT, and we've understood that fluid dynamics is stuff that is equilibrated patchwise. A patch is a local concept. It's a local. It surrounds a point on the boundary. But ADS-CFT is holographic. Okay? So in order to build a metric that reduces to patchwise local equilibrium, we need to foliate ADS space into tubes. Okay? So we need to take these tubes and extend them somehow. That's the only natural way of extending this patchwise idea of fluid dynamics to a construction in gravity. But now that we've done this, you see there's an important ambiguity. The question is, what is the shape of these tubes? Okay? Now in that metric, what shape have I chosen? Okay? The shape I've chosen is best represented in a Penrose diagram. So suppose we take Penrose diagram of ADS space. I've got this black brain. Okay? I take my patch here and I'm drawing a tube. Where does this tube go? Well, these tubes are along lines of constant time, constant Schwarzschild time. As you all know, no line of constant Schwarzschild time passes either of the event horizons. Schwarzschild time is infinite on both event horizons. So these tubes must be doing this. They must be meeting the bifurcation point. That is true. Okay? So the tubes I've chosen to foliate my space in are these tubes. Now if you think about this construction, this sounds very weird. It sounds very weird because we're trying to make the dual to hydrodynamics. Hydrodynamics is a causal theory in the sense that if you've got some fluid flow, then you hit it by an operator. The effect of that hit propagates only in the future. But these tubes don't respect that light cone structure. This is an immediate physical reason for knowing that what we tried to do was wrong. There's actually a technical manifestation of that I'll very briefly tell you about, that was explained to me by Javi Rial actually, but he's not here. Okay, that technical manifestation goes as follows. Look, this metric here with constant values of u, mu and t looks bad at the horizon, but isn't bad. The apparent badness is a coordinate singularity. Okay. On the other hand, if you take this metric and fool around with it a little bit, for instance by making u mu a function of x, or t is a function of x, what was a coordinate singularity could become an actual physical singularity. And that's in a slightly subtle way what happens to these metrics. So if you write down such a metric, forgetting about whether it solves Einstein's equations or not, it's just it's a metric with strange singularities at funny places. Okay. You know, once you get into writing down singular metrics, you don't know what the rules of the game are, so this also sounds bad. Okay, so this doesn't sound like the right idea. Okay, is there a way of fixing this? Well, let's try to fix the problem first by appealing to the technical problem. The technical problem was that we had spurious singularities apart from the expected singularity of the black brane. How do we fix that? You see, the problem was that the apparent badness of the event horizon became a real badness when we fooled around. So let's try to work in coordinates in which the event horizon is manifestly fine. Then if we fool around, everything will be manifestly fine. Okay, so let's do that. Okay, so in order to do that, what I'm going to do is the board visible from here on to everyone? Okay, what I'm going to do is now move to coordinates in which the bad features of this metric are not there. Now, what was bad about this metric? One thing that was really bad was that it blew up at r equals at the event horizon. The dr squared term blew up. How do we fix that? Well, let's move to coordinates. One way of doing it, this is the way invented by Eddington and Finkelstein, is to move to coordinates in which the coefficient of dr squared is 0. Then it can't blow up. Okay, so let's do that. So we've got ds squared is equal to minus f of r dt squared plus dr squared by f of r plus r squared dxi squared. Now what I'm going to do is to move to a new coordinate v. So v is equal to t plus g of r. And I'm going to choose g so that the coefficient of the dr squared term goes to 0. In these new coordinates, let me call it t is equal to v plus g of r. In these new coordinates, what's the coefficient of dr squared? Well, clearly it's dr squared is what it was, so 1 by f of r, plus what we get by acting twice here, so minus f of r g prime r squared. Is this clear? If I want to set this to 0, I get the equation that g prime of r is equal to plus minus 1 by f of r. Okay? So I find g of r by integrating this equation. Once I've chosen g of r in this manner, what does the metric become? Well, the dr squared term is 0. The dv squared term is whatever dt was, dt squared is. So we get minus f of r dv squared. But now we have a dv dr term. The dv dr term comes from taking, one dv here, in one of the two dt's taking dv, and the other of the two dt's taking the dr from here. It becomes, there was a minus, so we get minus plus 2 dv dr g prime of r by f of r. Sorry, this is so far just minus f of r. But this, by this equation, is simply minus plus minus plus 2 dv dr. Okay? And then you have your remaining r squared dxi squared. This is the, it turns out that we want to choose the guy with plus. This is so that we're dealing with Eddington-Finkelstein coordinates adapted to ingoing rather than outgoing geodesics, so that the future rather than the past event horizon of our solutions will be kept manifestly regular. Okay, now that we have this solution, okay, now that we have this solution, what we do is once again boost it. So we get a boosted version of the solution, so minus f of r, u mu dx mu, the whole thing squared, minus u mu dx mu dr, minus 2 dr, plus r squared p mu nu dx mu dx nu. This is the uniformly boosted version of that solution. It's also an exact solution of Einstein's equations. And then we play this game on that solution. On this solution here, we replace u mu goes to u mu of x, and t goes to t of x. Please.
Generically, this will spoil the past event horizon. You'll have a singular past event horizon.
Yes. You know, that statement is dual to the fact that any solution of fluid dynamics, if continued to the extreme past, blows up. You know, fluid dynamics is viscous towards the future, but is anti-viscous towards the past. So this has the fact, you know, what fluid dynamics answers the question that you set up a well-defined initial condition and then follow its future evolution. That's the kind of question for which you should ask fluid dynamics questions. So what you say is right, but it's also expected. Okay. Okay, excellent. So now what do we have to do? Okay, now I've written down this metric, and it's clear that it doesn't have the singularity problem that Javi Real told me about, because the metric and its curvatures and so on are manifestly okay even when u is a function of x and t is a function of x. Does it have the physical problem that we were worried about before? No, it doesn't. Because sorry, when you look at these tubes now, lines of constant v go along null ingoing geodesics. So the tubes that we're using are adapted to null ingoing geodesics. So they have exactly the kind of causal properties we expect from the causality of fluid dynamics. So this is the nice kind of thing. Both problems are solved with one maneuver. Okay? So we'll take that as a sign that we're on the right track and proceed. Okay, good. So far we have some intuition that solutions of hydrodynamics are going to be dual to metrics that look somewhat like this. But you know, that's not good enough. We don't want just some metric that we write down. We want a solution to Einstein's equations. Okay, is this a solution to Einstein's equations for an arbitrary velocity and temperature field? Of course not. However, this.
It's a technical question. I mean,
Yes.
Everything you're doing now in these coordinates, you could transform back into the other coordinates.
Yes, you could transform back into the other coordinates.
So
but it will not.
But then the procedure would not be that different.
No. But you see, this metric. Okay, good. So it's a good and important question. If everything was constant, you took this metric and you transformed back to the earlier coordinates, you would get just the constant metric in the earlier coordinates. Okay, but this metric with u mu as a function of x is not coordinate equivalent to the earlier metric with u mu as a function of x.
Yeah, well, it would be some complicated function of x and r.
You would have a lot of corrections that depend on derivatives of u mu. Okay, so you could try to go to this gauge which says dr dx mu is equal to 0. That's a well-defined procedure, but in doing that, you generate lots of terms that depend on derivatives of u, and these derivative terms are singular at the horizon. Okay, so these two spacetimes as spacetimes are extremely different, as is clear from the fact that one of them is singular, the other one is not. Okay, when u and t are constants, they're the same space-time. But when u and t are varying, no matter how slowly, there is a part of space-time in which they differ enormously. So one has a singularity, the other one doesn't. Okay, so as physical spacetimes, they're enormously different starting points. So the important thing is that it's not an important question. The important question is not about which gauge you're using. It's about what your starting point for what spacetime you use as a starting point for a perturbative expansion. Okay, these are distinct spacetimes, very distinct. They differ by a singularity. Please.
I guess that along with Julian, going back to what Julian asked, I guess that if you find a solution in those coordinates, which is perfectly smooth, as you will demonstrate, then you can always change coordinates and consider another foliation where you have where your constant say t slices are
absolutely. Absolutely.
And then I guess that this would be sort of similar to the earlier picture.
It would be similar to the earlier,
but it would be regular, right?
It would be regular, but how could it be regular? Because the earlier configuration was singular. So what must be happening, and what is happening if you try it out, is that it's the earlier thing plus derivative corrections, such that these derivative corrections are blowing up at the horizon. So this blow up cancels the singularity of the earlier singularity. You see? So you could do the whole thing in that earlier gauge, but not with this starting point. With this starting point plus singular corrections. You never think of doing that. So it's not a question of which gauge, it's a question of what is the right starting space-time. That's the question. Okay? Okay, excellent.
So sure. Does it matter that you're doing this coordinate transformation on the boundary as well? So in the dual theory, you've also done some.
Okay, actually we're not doing the coordinate transformation on the boundary because f of r goes like 1 by r squared at large r. So this coordinate transformation dies off at large r. So v and t are the same on the boundary. It's a good question. Thank you. Okay, other questions, comments? Excellent. So now that we've got the starting point clear, we're just going to turn the crank. Okay, what do I mean by that? Look, this metric here is not a solution to Einstein's equations, as we've repeatedly emphasized. But it is a solution to Einstein's equations in one circumstance, namely when temperature and velocity fields are constant. Okay? So, perhaps it is an appropriate starting point for a perturbative expansion of solutions to Einstein's equations when temperature and velocity are slowly varying. Okay? So that is the achievement. The achievement is to write down the appropriate starting point for a perturbative expansion. Now, just for those of you, well, all of you know this, but anyway, perturbation theory is an art. Okay? It's an art that consists of choosing the right starting point. You're looking for a solution here. You start here and try perturbing, you're sunk. Okay? But you start here and try perturbing, you'll do it. So the art in perturbation theory is to guess the correct starting point. Once you've got the correct starting point, you turn the handle. Okay? But if you get the starting point wrong, no matter how much you turn, it doesn't work. Okay? So this is the most important thing in what I've told you. This is the right starting point for the perturbative expansion. Okay. Now what we want to do is to find the right solution. So we suppose it's true that there's a solution to Einstein's equation, okay, which takes the following form. I'm going to explain this. Okay, so there is some metric that solves Einstein's equations order by order in a derivative expansion such that the first term in that expansion is this g. Now I want to do this order by order in derivative expansions, and I want to have a convenient way of making that precise. So what I do is the following. Look, I look for solutions such that they're not functions of x, but of epsilon times x, where epsilon is a small number. Why do I do that? Suppose I've got a function whose scale of variation is 1. in its argument. So then for that function to change significantly, its argument has to change by 1. But if its argument is epsilon times x, then x has to change by 1 over epsilon. Okay? So by writing down a reasonable function with a reasonable scale of variation, but making it a function of epsilon times x, I'm making it a very slowly varying function. Okay? So if I, just as a formal device, regard every function in the game as a function of epsilon times x and work in a power series expansion in epsilon, then I'm doing a derivative expansion. Okay? I'm working in an expansion in 1 over distance. Okay? So I look for solutions of Einstein's equations that are functions of epsilon times x, such that the 0th order term in this equation is what I wrote down here. This is not a solution to Einstein's equations, but I'll try to correct it by adding epsilon times g1 of epsilon times x plus epsilon squared times g2 and so on, and see if I can find genuine solutions to Einstein's equations. That's the game I'm going to play. Any questions or comments about this? Okay, so just like in fluid dynamics, before we start our work, we have to get irritating complications out of the way. Okay, now the first irritating complication is that gravity is a gauge theory. When you have a gauge theory and you're trying to solve equations of motion, you can either work in a gauge invariant manner, which is often very difficult, or you can fix a gauge. Okay, in this game, after a lot of trial and error, we hit upon a gauge that is very convenient. Okay, we decided to fix the gauge so that g mu r is equal to minus 2u mu x. And GRR is equal to 0. Well, what can we say about this gauge? Well, firstly, we have 5 coordinate redefinition freedoms. Okay, there are 5 gauge conditions here, 1 plus 4. The second thing we can say about this gauge is that our starting solution respects it. Our starting point in perturbation theory respects it. The third thing that we can say about this gauge is that it's very unusual. It's very unusual. It's like a background field gauge in gauge theory, because it's not a gauge that we choose once and for all. It's a gauge that depends on the solution we're looking at, because u mu of x is the particular solution we're looking at. So it's not like we're looking at all solutions to hydrodynamics in the same gauge. We adapt our gauge to the solution that we will study. This is an unusual thing, but it greatly simplifies analysis. Okay, we tried various more standard gauges first, and life was tough. Okay, this greatly simplifies analysis. This is one of these things. It doesn't make a difference physically what gauge you choose, but in practice it will make a huge difference. Okay, so this is the gauge I'm going to adapt. Okay, now having adapted this gauge, what do we want to do? We take this expansion, plug into Einstein's equations, Rmn plus whatever, I think 4 times gmn, some number which I can't remember, times gmn, which you get by varying Einstein's the action I told you about, is equal to 0. And what do you get? Well, you don't get anything. You get some power series expansion in epsilon. You get no term at order epsilon to the 0, which is the statement that this metric solves Einstein's equations when t and u are constants. But you get something, you get epsilon times something plus epsilon squared times something, and blah blah blah. And we want to try to set all of these terms successively to 0. That's the game of perturbation theory. Okay. Now, I want to examine the structure of these equations. I want to examine the structure of these equations in various ways. The first thing that might occur to you about these equations is that the number counting doesn't seem to work. Once we set our gauge, how many degrees of freedom, how many unknown components of the metric do we have? Well, we started out having 5 in a 6 by 2, that's 15 components of the metric. We set 5 gauge conditions. What's left is 15 minus 5, that's 10 components of the metric. Okay? how many equations do we have? The number of equations that we have is 15 Einstein equations. How can you solve 15 equations for 10 variables? Now, this is not a question that is unique to this situation. It's a question that you address whenever you try to solve a gauge theory, and you all know the answer. The answer is that of 15 of Einstein's equations, okay, 5 of the equations have a distinct logical role from the remaining 10. They're constraint equations. They're not equations that tell you how to take data and evolve them forward in time. They're equations that constrain data. Okay? Now, equations can be made dynamical or constrained depending on your slicing. And the slicing that is clearly of relevance to us, as we will see as we proceed, is a slicing in radius. So when I talk about a constraint equation or a dynamical equation is something that takes data at one slice an hour and evolves it forward an hour. Constraint equations constrain data on slices an hour. Okay? So as we will see, the constraint equations and the dynamical equations have a different logical status in our procedure. Okay. Let me start by first looking at the 10 dynamical. Okay, let me first start by looking at the constraint equations. Suppose you take Einstein's equations, do a radial slicing in ADS space, and okay, there's one more thing about constraint equations I should say. The thing about constraint equations that's important is the following. Look, suppose you've got equations that constrain data, and then you've got dynamical equations that take this constrained data and evolve it forward. It had better be true that the forward evolved values of the data obey the constraints on this new surface. This had better be automatic, otherwise you've got an inconsistent set of equations. Yes?
Sorry to interrupt.
Yes?
So you have your initial data on a null slice?
No, just lines of constant r.
Is this like an initial value problem on a null slice, or it's an initial value problem on a...
Well,
but
this is on a null slice. I will be evolving it for, let me think about that. It's a line of constant r and a line of constant r. Yes, so the v direction a constant. No, it's not null. It would become null only at the horizon. This data is, so suppose I've got a line of constant r in this metric. So r is constant, so we take this away. This is the slice of the metric.
Okay.
Yes, I'm slicing my surface.
How do you know that this is a well-defined...
We're going to solve it, okay? We'll find a solution, so it had better be well-defined. I mean, okay.
There are boundary conditions which make it well-defined.
Yeah, okay, I mean, I'm sure it's a good question, but yeah, how do I know it's well-defined?
Don't you take your initial state at the constant t?
What?
Constant t is your initial data, right?
Constant t. No, okay, good. For the purposes of solving Einstein's equations, that's what we would do for hydrodynamics eventually. No, but for the purpose of solving Einstein's equations, I'm going to think of this. I'm going to solve Einstein's equations in a convenient slicing. Okay? This is not a physical slicing, it's just a convenient slicing. The convenient slicing is slicing it along lines of constant r. So let me try to address this question. So the discomfort is that we're moving in a spatial direction.
Exactly. This tends not to be a well-defined initial problem.
This tends not to be a well-defined initial value problem.
Excuse me, why is it different between
time and space? I mean, if you have an initial value and if you try to integrate from the boundary, there's a classical theorem that tells you that you generically find singularities somewhere in the middle.
These null congruences? But you see, this will probably happen, but for fast enough motion. We're going to explicitly solve the equations and not find these cusps. So I would have to ask you why we don't find them, but we don't.
Yeah, but I'm happy with that.
Yes. Okay. Yes. Okay. Okay. Fine. Excellent. So excellent. Fine. So what we do is to plug this in, and we would open the constraint equations. So now suppose you take, so as I said, the constraint equations have this property that we start with constraint data, you evolve forward by dynamics, the constraint is automatic at future slices. Okay, this is a property of Einstein's equations, property of Maxwell's equations, which is very easy to see. It's a little more difficult to see in Einstein's equations. That's of course true, because the equations are consistent. Okay, what does that mean? In order to solve Einstein's equations, we don't need to solve all of Einstein's equations everywhere. We have to solve the dynamical equations everywhere, but it's sufficient to solve the constraint equations on one slice. Constraint equations on one slice plus dynamical equations automatically imply Einstein's equations are everywhere solved. This is true in every gauge theory, it's true in Einstein's equations. Okay? So, as far as constraint equations go, we will only worry about solving them on one slice, because we'll also be solving the dynamical equations. Well, there's a convenient slice on which you can solve these equations, namely r equals infinity. Okay? That's where the field theory lives. Okay? So you can ask, what do the Einstein constraint equations evaluate to at r equals infinity? Now those of you who have spent time studying the ADS-CFT correspondence know the answer. It's famous generally in ADS-CFT, or generally for people who studied anti-de Sitter space carefully. And the answer is that the Einstein constraint equations just evaluate to the conservation of the Brown-York stress tensor, as Finn Larson knows very well, on these large R slices. And in the language of ADS-CFT, where 4 out of the 5 constraint equations simply evaluate to the conservation of the stress tensor. Okay, they simply assert the conservation of the boundary stress tensor, dual to your solution. So the constraint equations are very special. Okay, they assert the conservation of the stress tensor. Of course, that should be the stress tensor conserved with dual to field theory. And this is how it happens. This is the mechanism for it happening in ADS-CFT. Now, these constraint equations are very special for us in our derivative expansion for a reason that is related, but I mean that is related to the fact that these constraint equations always come with a boundary derivative. So remember, so now suppose we're trying to do this expansion, this boundary expansion, we're trying to find all the terms that we get in the equations at order epsilon. From the constraint equations, we get no terms that depend on G1 or G2, because G1 automatically has an explicit epsilon, and the derivative would pull out another epsilon. So, at first order in this expansion, the constraint equations are entirely some statement about G0. They do not depend on G1, G2, and higher order G in that expansion. Is this clear? This is a very important statement. Okay? So in this perturbative procedure, the constraint equations do not satisfy the role of determining higher order terms in your perturbation. What they instead do is constrain what your starting point for perturbation theory could have been. Okay? Now what constraint do we get? What constraint do we get? What does this evaluate to explicitly? It's a simple matter to take G0 and to evaluate the boundary stress tensor. In fact, you sort of know the answer because, you know, since if we evaluate it and ignore terms that are proportional to epsilon, derivatives, it has to be the same answer as if you had just a uniform brane. And if you had a uniform brane, the answer is well known. It's T mu nu is equal to T to the 4 n squared times some number times u mu u nu plus eta mu nu. Okay, all properties of this answer can be deduced immediately on general grounds. The stress tensor in ADS-CFT is famously traceless because it's conformal field theory. That fixes the relative coefficient between, oh, it would if I did it right, the relative coefficient between this term and this term, because this term has trace minus 1, this term has trace 4. Dimensional analysis tells you that you have to have T to the 4. 'T counting, or the fact that you have 1 over G, tells you the n square. And then there's a number that you can calculate using the details of ADS-CFT. That number has this famous 3/4 factor compared to free Yang-Mills. But we're not if we forget about such numbers for a moment, just to get the basic point, this is the value of the stress tensor. Just one second. And then this equation asserts the conservation of this perfect fluid stress tensor. So what does it say? It says that this perturbative expansion that we're setting up cannot start from an arbitrary velocity and temperature configuration. The starting point for this perturbative expansion has to be a velocity and temperature configuration that obeys the equations of motion of perfect fluid hydrodynamics, with the perfect fluid having the equation of state of n equals 4. Yes?
This is the stress tensor for a conformal theory, but doesn't a finite temperature destroy conformal invariance?
No, it's the stress tensor at finite temperature for a conformal theory. You see, for instance, suppose you wanted to ask the question, what can the energy density of a conformal theory be at temperature T? Okay? So there's no intrinsic length scale in the problem, but there's a length scale in your state, namely the temperature. So the energy density has to be T to the 4. Okay? So you see, an invariance of a theory constrains the dynamics even of states that are not invariant under that invariance. That's what's happening. Okay, excellent. Other questions?
Aren't you short of one constraint? There are 4 constraints.
Yes, that the last constraint is related to forcing the stress tensor to be traceless. And yes, so this last constraint is also, once we put this, is also automatic given the dynamical equations. It forces tracelessness. So that doesn't give us anything useful. Thank you. Okay, other question. Okay, good. So we've learned our first important lesson. This whole procedure cannot start from an arbitrary velocity and temperature configuration, must start from velocity and temperature configuration that obeys the equations of perfect fluid hydrodynamics. Once we have such a configuration now, though, we want to now go ahead and correct it. Can we find the solution? Okay, so let's try. So now, what is the structure of the 10 dynamical equations and that last constraint once you have tracelessness? Okay, it's mixed up for me. The structure of this constraint is as follows. There's some operator, let me call it O, acting on G1 Mn. Okay, some linear operator. It's a linear differential operator, and I'll tell you more about it. It's equal to S1n at first order in epsilon. This represents all parts of the equation that care about G1. Clearly it's linear in G1 because we're working to order epsilon. This represents all parts of the equation that don't have a G1 in it but act by taking derivatives on G0. Okay? So it's some linear differential equation with a source. Homogeneous piece and a source. That's the structure of the equation. Now we have to think about this operator O. What kind of operator is it? It's a differential operator, but there's something very important here. It's a differential operator which has derivatives only in R and not in the x mu directions. Why is that? Well, it's obvious. If you had an x mu derivative, you would get 2 epsilons, because there's one explicit epsilon in multiplying G1, and you would get an additional epsilon by the derivative acting on G. So this operator is a linear differential is an ordinary differential operator. Linear ordinary differential operator. The derivatives act only in R. What does that mean? It means that the equations that we have to solve tube by tube. At every given value of x mu, you solve an ordinary differential equation and patch up the whole solution together. So what we're doing is taking a complicated nonlinear partial differential equation and breaking it up, and doing perturbation theory. The perturbation theory does 2 things, one of which is standard. It linearizes the equations order by order. That always happens. That's the role in life of perturbation theory, to make nonlinear equations linear. Okay, that's not new. What's interesting here is that because of this, we're not just doing an amplitude expansion. There's an amplitude plus coordinated with a long wavelength expansion, which takes nonlinear partial differential equations and converts them into an infinite set of linear ordinary differential equations. Okay? This is the locality of hydrodynamics. that we can solve for the tubes independently of what else is happening here. If this wasn't true, the whole idea would have been wrong. Okay, it's the fact that stuff here doesn't care about what's happening, what stuff here is doing. Stuff here determines some part of the space-time autonomously.
Doesn't it break down with order epsilon squared?
No.
You now have the derivatives in the I direction, which gives you a power of epsilon.
Yes, but now let's see how this would work at order epsilon square. Suppose we are working at order epsilon square. What we've already determined G1. So what we need to do is to determine G2. G2 has 2 powers of epsilon. So at every order in epsilon, you're always solving the same, well, a very similar linear differential equation. It's the same homogeneous part, in fact, only a different source. And the source is determined by knowing the solution at other orders. Okay? Great. Now, how many such linear differential equations do we have? You know, a really beautiful version of the aspect of this problem is that that it's not a problem where you can just say this can be solved. You can actually solve it. Okay. Now it's rare that you can solve equations. Now, why could you solve it here? Well, you see, even though we've reduced it to ordinary differential equations, we've got 10 ordinary differential equations, and at first sight it sounds like all of them will couple with each other. What hope in life do you have of solving 10 coupled ordinary differential equations? Give up, right? The point is here that these equations are not all independent and they're not all coupled. In order to say that, we use the fact that this problem, as we've seen, is local. In order to solve the equation at one point, you don't care what's happening elsewhere. So at any given point, we can boost the solution so that the velocity becomes 1, 0, 0, 0. And actually, it's convenient to scale the solution so the temperature becomes 1. That's not very important, but you can do it. Okay? Now, about this point, the velocity vector is u mu is equal to 1, 0, 0, 0. And then, in the unperturbed solution, there's an SO3 invariance. This is exactly the same SO3 invariance of tangent space configurations of hydrodynamics. Okay? So now, all of the unknown metric functions are organized into representations of this SO3. Let's see how they're organized. You see, there was the R component of the metric, but we've completely determined everything in R. There's the V component in this gauge, and then there's the X component, X1, X2, X3. R, V, X1, X2, X3. A gauge fixes all of this, so there's nothing here. There's nothing there. Okay? And for the rest, there's this guy, which is the 5 plus 1. There's this guy, which is the 1, and this guy, which is a 3. Okay? So our variables have the following transformation property under symmetry that the problem respects. Okay? So that tells you that instead of having to solve 10 coupled linear differential equations, you only have to solve 4 different linear equations, and only 2 of them can couple. Okay? So the equation for the 5 is just one equation, the equation for the 3 is one equation, the 2 equations for the 1, you need a little luck there, but you have that luck. Okay, so you can solve it.
It's in the first order now.
Well, this is at first order, but there's something important. The important thing is that this operator here at every order is the same. What changes is the source term. Now, these differential equations are simple enough that it turns out you can solve them for arbitrary source once and for all. So all differential equations that you will ever encounter in this game at 37th order, for instance, you've solved. So now it's just an algebraic procedure. Okay? Excellent. So now there's just one more. Oh, I'm almost out of time. There's one more thing that I have to. I should have gone a little faster today. I'm sorry. There's one more thing that I want to explain to you, and then I'll make a few summary punchlines. Okay. The last important qualitative thing about solving these equations that I want to explain to you is the following. The really important thing is that these equations not only can be solved but have a unique solution. Okay? That there is no free data in the solution once you impose all physical constraints. What are the physical constraints that we're going to impose? First, we're going to impose that these solutions are normalizable. Second, we're going to impose that these solutions actually correspond to velocity u mu and temperature T as defined by our Landau gauge condition. So that u mu and T are not just parameters characterizing the equation, but they're actually the velocity and temperature of our fields. So we know what solution we're talking about. These are the trivial things. The really important thing is that we're going to demand that our solutions have regular future event horizons. We're not going to allow any solutions of Einstein's equations that develop a singularity that is not shielded by a regular event horizon. That is our rule. Such solutions we declare illegal. Whether that's correct or not, we could have a long debate about, but this is our rule, and we seem to land on our feet. Okay? We're suspicious of singularities, we won't allow them. We're only going to look at regular solutions. I want to show you how that works. Okay, so in order to see how that works, let me show you what you get for solving the differential equation in the 5 sector. It turns out, actually, I could probably show you why. Something that some of you are familiar with is that if you've got, you're solving Einstein's equations in a black brain kind of background, and you look at the equations for modes with polarizations orthogonal to the brain, then those equations reduce to minimally coupled scalar equations. Okay? So for this tensor mode, the mode where the legs are like this and traceless, we get a minimally coupled scalar equation in our background. The minimally coupled scalar equation, you don't have to rely on me, we can just derive. So let's see. So our metric here was ds squared is equal to minus f of r dv squared plus 2 dv dr plus r squared dxi squared. Okay, so the minimally coupled scalar equation requires square root g, which in this case is r cube, and it requires g rr, g rv, and g vv. Now it's not a difficult thing to invert this metric and to check that g rr is equal to f of r, g rv is equal to 1, and g vv is equal to 0. Upper triangular metric when inverted, matrix when inverted becomes lower triangle. Okay, so now plugging this in, we get the equation d by d. You remember, we get the minimally coupled scalar equation, but we keep only the radial derivatives because everything else is higher order than epsilon. So you get d by dr of square root g, so it's r cube, times f of r, times d by dr of alpha ij, that's the unknown component of the metric, the tensor part of G1, okay, is equal to some source. The source requires a calculation, okay, but it turns out to be minus 6 r squared sigma ij, where sigma ij is del ivj minus plus del jvi is the non-relativistic limit of sigma mu nu. Is the non-relativistic limit of sigma mu nu by 2 plus del dot v delta ij by 3 minus. Okay, where vi u mu is equal to, in small fluctuations around, at the point of interest we took it to be 1, and neighboring points it's 1 vi. Okay, to lowest order. Okay, that the source here had to be sigma ij was obvious. You see, the source is built out of G0. G0, the only data in G0 is the velocity field and the temperature field. You have to have something that transforms in the 5, built out of one derivative of velocity and temperature fields. This is a problem we analyzed yesterday. There's a unique object, it's the shear tensor. So that you would get sigma ij in doing this was obvious. Okay, the only thing that required a calculation was what comes here. Turns out to be minus 6 r squared. It's a very innocuous number. Okay, now that I have this, I want to solve this. Now that I have the equation, I want to solve the equation. Okay, I'm solving it to make a point. I want to explain why we get unique solutions. Okay, see, when we solve this, this is easy to solve. We just have to integrate. So we get r cube f of r d by dr of alpha ij is equal to minus 6r squared sigma ij dr. Okay. Now, this integration looks like it has an integration constant. This integration constant is an integration constant as far as r derivatives are concerned, but of course an arbitrary function of x mu. So it looks like it introduces one function of x mu ambiguity in the solution. That's not right actually. That's not right because f of r is 0 at the horizon. Okay? This object here would be non-zero at the horizon. Okay? Unless I choose the integration constant so that I integrate from the horizon to r. What does this mean more physically? Of course, we could choose any starting point we want. We could add plus constant here, but then that would ensure that this alpha is a singular solution, because its derivative would be 1 by r. It would have a logarithmic singularity. Okay. Our basic rule is we don't allow singularities. Okay. So the maintaining the regularity of the future event horizon fixes this integration constant, the first integration constant. Okay. Then once we've got this, we get alpha ij is equal to 1 by r cube f of r, then another integral times this function wherever it is, and this integral, it turns out we have to do from minus infinity to r, and the thing that fixes that is the requirement of normalizability at infinity. So these two conditions, the condition of regularity and the condition of normalizability at infinity, completely determine the solution. Okay? There is no free integration constant in the solution. Given the starting velocity configuration, this correction is uniquely determined. Okay, so just 1 minute and I'll stop. This procedure can be carried on to arbitrary order. At each order, you determine the correction to the velocity and temperature uniquely, correction to the metric uniquely in terms of the data that you put into your solution. What changes order by order? What changes order by order is that at each order, the integrability condition for your starting solution changes a little bit, because at nth order, what you need, the constraint equations become the integrability condition for the stress tensor evaluated to nth order. Now, you see, how do we get, so for instance, suppose we were going to do the second order calculation. Okay, what would the starting integrability condition be? We've found the first correction to the metric. We've just done it here. Now we take this first order corrected solution, write it down. I'll write it down next time in full detail, but you write it down and you evaluate the stress tensor from this first derivative corrected metric. It turns out that in addition to the perfect fluid piece, you get a sigma mu nu term from this term that we just evaluated here, times the coefficient. Your integrability condition now is conservation of this modified stress tensor. Solving that allows you to compute what's happening at second order. Then you solve the dynamical equations at second order. By doing that, you get a slightly corrected stress tensor at second order. Solving that allows you to go to third order, and so on. So this procedure generates a unique solution to Einstein's equations, given a solution to the equations of hydrodynamics, and in a very beautiful way, self-consistently generates the constitutive relations of hydrodynamics as you solve these equations order by order. Okay? So that's it for now. I'll come back to this in my last lecture tomorrow.
Any questions, please? What happens with the Weil anomaly? Do you get it from the solution, or because this is in 4-dimensional boundaries? So.
Yeah. So now to explicitly see the Weil anomaly, you'll have to go to fourth order, and we haven't explicitly gone to fourth order. So, but I mean, it should appear. It should be that the stress tensor has the form that it's traceless apart from this. Is this something you've looked at? You've looked at Weil anomalies? Okay, it should appear, but we haven't explicitly seen it because we've not done explicit calculations to fourth order.
Does it mean that the form that you're solving Einstein equation makes some assumption about correlators of velocity of the fluid?
I don't think so. I think that this is the right gravity solution for any solution of hydrodynamics. Then the question of what allowed solution of hydrodynamics is a completely distinct question. So now if you've got some turbulent hydrodynamic flow and it has its own velocity correlators because of some funny solution, that looks like a second distinct question. What we've done is establish a map. You give me a solution of hydrodynamics, I'll give you a solution of Einstein's equations to the same order in the derivative expansion. It's a constructive map. And it's a one-to-one map. That's very important. It's not an into map. It's not like, it's that this map is locally invertible. This map is locally invertible because of the uniqueness of our procedure. That is, let me say this again. Given a solution to hydrodynamics, I give you a solution of Einstein's equations. Now, starting with the solution of Einstein's equations, you could ask, is there a small change in Einstein's equations? What is the set of small changes of solutions to Einstein's equations that are also long wavelength? And the answer is that any small modification is just a modification to a neighboring fluid flow because of the uniqueness of our procedure. So it's establishing the identity between these two dynamical systems in this particular limit. But it's not doing more. It's not telling you about either system. If you want to understand something about solutions of fluid dynamics, you'll have to know something independently about solutions of gravity. If that was the question.
But also in a turbulent flow, for instance, you might expect that these null rays cross, for instance, and that this procedure is no longer applicable.
Well, you'd have to have the flow becoming singular somehow for that to happen.
But turbulent flow might be enough. To which extent can you learn about, say, open questions like turbulence by studying gravity? I think this seems to show that, unfortunately, not much.
Really? I don't think I agree with that. Turbulent flows aren't supposed to be singular at a microscopic level. Meaning, you look at them, they look very jiggly, but I think it's assumed that any given solution of hydrodynamics is just some analytic thing that's moving very crazily. As long as it's, the solution is smooth on some effectively small wavelength, this should work. Okay.
What about shock waves?
Yeah. Shock waves might be bad. So if you have something with a real singularity, that might be bad. Okay. Let me turn your question around. There are two famous questions of hydrodynamics. There's the question of finding the correlation functions of turbulence, and there's the question of winning $1 million. Which is the question of establishing whether regular initial conditions of the Navier-Stokes equations develop singularities in finite time. Okay? That second question may be hard to address from this point of view, because if something is going to become singular, it goes out of our regime. Yes.
One last question, Jim. Is there an easy way to see that your boundary condition in the infrared is equivalent to the infalling boundary condition using Hubble's formula?
Yes, I think it is. For instance, one thing you can do, our procedure gives you, and I should have emphasized this, the really nice thing about our procedure is that it gives you the dual to any solution of hydrodynamics, not necessarily linear. But it gives you the solution to any solution of hydrodynamics, so then you can look at what it becomes for linear solutions. And there it becomes exactly the ingoing solutions that everyone else uses. Yes. It's sort of clear, it's also clear physically, I could explain to you why.
Let's thank Shiraz for a very nice lecture.